So, as we saw before, if we've got eigenvalue, eigenvector pairs for A, then we can construct a non-trivial solution for the homogeneous system x prime equals ax by just multiplying e to the lambda t times v. And the proof for that actually is really straightforward. If lambda v is equal to av, then multiplying through by e to the lambda t, we have lambda e to the lambda tv equals e to the lambda t av, and I can rewrite the 1 on the left hand side as being the derivative of e to the lambda tv, and I can rewrite the 1 on the right hand side as a times e to the tv, lambda tv, because it's a scalar, so I can put it anywhere I want, and then that's exactly x prime equals ax for an x of this form. So super easy. And then so if A is n by n and has n distinct eigenvalues, then the general solution is just going to be a linear combination of these guys. So in other words, by our vector space basis arguments, we have an independent set of n vectors, so it's a basis. Oh, I guess the key point here is that if you have a set of eigenvectors corresponding to different eigenvalues, it'll be a linearly independent set. Okay, so let's look at an example of how this works. So suppose we start with the system x1 prime equals x2 plus x3, x2 prime equals x1 plus x3, and x3 prime equals x1 plus x2. So each one, the derivative depends on the two that are not it. So let's see. So I can convert this into matrix formulation by saying x prime is going to look like 0, 1, 1, 1, 0, 1, 1, 1, 0. And so now we can go ahead and solve this by looking for eigenvalues and eigenvectors. So if I look for a determinant of a minus lambda I, this is going to be, see, I'll have minus lambda 1, 1, 1 minus lambda 1, 1, 1 minus lambda as my matrix. Take the determinant of that bad boy, and we get minus lambda cubed plus 1 minus negative lambda minus negative lambda minus the negative lambda. So this, I'm doing this product here plus this one, and then minus negative lambda minus negative lambda minus negative lambda. And so this is minus lambda cubed plus 3 lambda plus 2, which factors as lambda minus 2 and lambda plus 1. Okay, and so in case you're wondering where this factorization, oh, I forgot a square, where this factorization came from, what I did is guessed and checked and saw that 2 is a 0 of this thing, right? So if I have minus 2 cubed plus 3 times 2, then that's 6 minus 8 plus another 2 is equal to 0. So that tells me that lambda minus 2 is a factor of this thing. And so then I can say, okay, well, let's divide lambda minus 2 into minus lambda cubed plus 3, 0 lambda squared plus 3 lambda plus 2. And so actually, you know what, let's just make those multiply it by minus 1 all the way through. And then let's see, so lambda squared, lambda cubed minus 2 lambda squared, 2 lambda squared, bring this guy down, minus 3 lambda. So I've got 2 lambda, oops, just 2 lambda, 2 lambda squared minus 4 lambda lambda minus 2 and then 1. Okay, and so then this factors as lambda plus 1 squared. Okay, so I've got my eigenvalues. Let's look for the eigenvectors. So for lambda 1, which we'll take equal to 2, I look at a minus lambda 1I, and it's minus 2, 1, 1, 1, minus 2, 1, 1, 1, minus 2. And row reduce this sucker. And I'll save you the pain of doing the row operations, but I got 1, 0, minus 1, 0, 1, minus 1, 0, 0, 0. So this tells me then that my eigenvector is 1, 1, 1, so the constant vector. So I have one solution, and that looks like e to the lambda is equal to 2 times t times this vector right here. Okay, carrying right along. For minus 1, we have a minus lambda 2 takes the form, let's see, 1, 1, 1, 1, 1, 1, 1, 1, 1. So that one's nice and easy to row reduce. And so from this, let's see, so I'm going to have two free parameters, say r and s. So then x1 is equal to minus r minus s, and x2 equals r, x3 equals s. So I get my, or actually, sorry, I should have been calling these v's or something. I don't know. Whatever, those things. So my second vector is going to look like minus r minus s, r, s equals r minus 1, 1, 0 plus s minus 1, 0, 1. So now I can take my, I got 2 out of this, so my x2 will be e to the minus t times negative 1, 1, 0, and my x3 will be e to the minus t times minus 1, 0, 1. Okay, now I've got my basis. So if I take the collection of these three things, so here's the first one, and then, here's the other ones. Then this guy here is my fundamental set, and my fundamental matrix is the one that's got e to the 2 t's down the front, and then minus e to the negative t, e to the negative t 0, minus e to the negative t 0, e to the negative t. So that's my fundamental matrix. And so let's see. So if I look at x times c, so my solution, this is going to be c1 e to the 2t 1, 1, 1, c2 e to the minus t minus 1, 1, 0, c3 e to the minus t negative 1, 0, 1. And so if I combine these all back together again in one thing, then I've got c1 e to the 2t plus c2 e to the minus t, oh sorry, that's a minus, minus c3 e to the minus t, c1 e to the 2t plus c2 e to the minus t plus 0, c1 e to the 2t plus c3 e to the minus t. Okay, and so this is my vector of solutions. And I just wanted to write it back this way because we started with x1, x2, x3 equations. And if you're coming from some word problem, some kind of a model, then it's good to be able to put back in terms of those, because maybe you're, whatever, modeling population biology of foxes, rabbits, and carrots, or who knows, something, right? And so those particular variables have meaning. And so then let's put things back in terms of those. And that's exactly what we get from this matrix system that we just created. So let me just replace that here. So we've got x1 is given by this, x2 is given by this, and x3 is given by this. That's our solution to the original system. And one last thing is that we talked often about how you can take an eigenvector, and so say we had one of these eigenvectors, minus 1, 1, 0, and you could just as easily have taken 1, minus 1, 0, or something like that, because you can change your arbitrary constants. And we also talked about how in differential equations, if you have an arbitrary constant and you want to change it to some other arbitrary constant, then that's totally fine, right? While we're in a system, however, you got to be careful about things like this, because you have the same C1 in different rows. So let me just show you what I mean. If we, let's duplicate this system here. And so now if I make a change and say, oh, you know what, right here, I don't like the minus sign, so I'm going to make this like positive C2 by absorbing the minus sign into C2. Well, that's not okay unless you also simultaneously change the positive down here to a minus sign, because it corresponds to this swap between these two eigenvectors. And the coefficients in the different rows have to stay in this ratio right here. So it's not okay to change the sign of one, but not the others.